insight into the connection between the speaker and the birthday boy. So I will have to leave those comments to the speakers. However, the topic and the name is certainly familiar to me from a discrete approach, from another discrete approach to quantum gravity. Quantum gravity. So the speaker is Jerzy Jurkiewicz, and we are going to hear about causal dynamical triangulations.
Thank you very much. I think I am the only representative of this approach to quantizing gravity using causal dynamical triangulations. And what I am going to say today is based on our work 4 years ago when we started to think about what could be the subject we could present on the 60th birthday of Jerzy Lewandowski. And the obvious question would be, is it possible at all to define a concept of a holonomy in the context of discrete manifolds, which we are typically using in our approach? So I will have to be excused for a very primitive introduction, where I will try to list a couple of trivial properties of holonomies. In fact, the special situation which we will have here is that we are dealing with manifolds which have a very fractal structure, which means that it's usually very difficult to define objects which would be continuous in the sense of general relativity, and so some thought has to be given and maybe some trivialities need to be repeated. Well, I will try not to mention much about causal dynamical triangulation model. I will only make some comments which are related to a particular question which I would like to discuss today. And in fact, what I will try to discuss would be something which would be an analog of the object which is used in QCD, which is Wilson loops, big objects, macroscopic objects. So this will be different than in loop quantum, loop quantum gravity. And I will show that, in fact, there is a quite interesting result which we have been able to obtain numerically in the study of such objects. Well, let me just remind you that holonomies are usually related with a notion of a parallel transport of a vector in the manifold, which is parametrized along a curve, which is parametrized by some gamma function parametrized by lambda. And then this quantity typically transforms at its endpoints in a way which is derived from the transformation of vectors. If we changed coordinates at the endpoints, we have also to modify this path-ordered product in a sort of trivial way, as it is here. The situation, as I told you, which we will be interested in, is a situation where, in fact, our manifold is composed from pieces on which, in fact, we cannot really define a global set of coordinates. What is rather a typical situation is that we have patches, and we can define a system of coordinates in each patch, but then we should somehow, if we want to make a parallel transport between these different patches, we should somehow define the way in which this connection is to be performed. So the simplest situation is just we have two such patches, neighboring patches, and let us assume that they have a non-empty cross-section, and that, in fact, we define somehow coordinates in U1 and we define them in U2, and that there is some intersection where we have two possibilities, either to use coordinates from the first or the second patch. And there we have somehow, if we would like to perform a parallel transform from any point in U1 to some point in U2, we have to connect the parallel transport defined in these two regions. And this means that in the middle, we have to change coordinates from the system x1 to the system x2. And this is just a trivial identity. Well, in fact, if we have such a solution, we can simply generalize it to any number of patches. And in fact, this is a simple formula with at each crossover between patches, we have to rotate our system. Well, it can also be shown that, in fact, this result does not really depend on how we choose this point in the middle between between U1 and U2, U2 and U3, and so on. We can define something like a Wilson loop, which traditionally is considered to be a closed, some holonomy along a closed path, which starts and ends at the same point, x1. And obviously, this kind of path-ordered product transforms locally at the point from which it starts. And it follows that conjugacy class of such a holonomy defines such a Wilson loop depends only on the path on which we perform this parallel transform. This problem, the concept of big holonomy loops, was not really studied in the context of perturbative quantum gravity. Of course, the situation is completely different in loop quantum gravity, when loops were promoted to be a fundamental object, and in fact, and they don't even need to be renormalized. But this, from the point of view of the analogy I would like to continue here, is different, and we would like maybe to see if we can use objects like Wilson loops in the context of discretized manifolds, which are typical for QCD, for our model of causal dynamical triangulations. And in some sense, as I will only try to explain to you, this model of causal dynamical triangulations is in some sense similar to a lattice formulation of QCD, where these objects have been studied, and in fact very effectively. So I will only say a few words about what is the model of causal dynamical triangulations. So the idea which is behind this model is that we will try to formulate a theory, quantum theory of geometry, rather than it's maybe too strong statement that it's quantum gravity. It's maybe quantum geometry. We treat spatial geometry as a quantum object, and in our approach, the states which are characterizing the three-dimensional geometry are discretized, and they are triangulated using regular tetrahedra. So that means that we have a tetrahedra with a common length AS, and we glue them in all possible ways. So in fact, different states corresponds to a different way we glue this tetrahedra together, and states are characterized also by the number of tetrahedra we use and how they are connected. These states, we assume, evolve in time, and they also evolve in a discretized time. So that means that between states there is a discrete step with some length at. Again, we assume this is a unique value. So, in this way, we try to calculate something which is analogous to Feynman path integral, which is amplitude, which would be amplitude to transform state with initial geometry to a state with a finite geometry. And the problem is how to calculate this kind of object. At this point, it's just formal, but what we assume is that, in fact, first of all, we restrict the class of geometries which we have to consider in this kind of path integral, which is that we assume that spatial topology of this manifold is fixed. Usually it's fixed and closed. And then we approximate this integral, this path integral, as a sum of over manifolds which can be constructed by gluing together states at different time layers. Well, the action which is here is needed to somehow put weight to each such configuration in order to calculate the integral. It can be used as it can be taken as a Hilbert-Einstein action, which is the simplest possibility which we have here. Well, if we want to glue together two states at different times, we need somehow to connect them. And in fact, in 4 dimensions, it turns out we need 2 building blocks. There are 2 types of 4-dimensional simplices, which in fact, in one layer, which is the T layer, they are all, they are based on this, they are coming from the state at time T, and then they connect to the state at time T plus 1 by time links. And in fact, to obtain a closed manifold in this way, it turns out we need only 2 types of simplices, which are 4-1 and 1-4, depending on how many vertices we have at each time level. And of course, we also have an inverted structure, 1-4 and 2-3, which are just a time reflection of this structure. Well, we are using the idea of Reger in this construction. So we assume that these simplices have a trivial geometry. Inside they are just trivial. If we glue together 4-dimensional simplices, they are always connected by 3-dimensional faces, which are actually tetrahedra. Well, just simple counting tells you that in 4 dimensions, each simplex has exactly 5 vertices. It also has exactly 5 neighbors, which means 5 faces, 10 links and 10 triangles, which are hinges actually in this construction. In this sense, we have this simple time evolution. We can analytically continue from from Lorentzian signature to a Euclidean signature, but still remembering the direction of time. So that corresponds to analytic continuation in the length of the time links to imaginary value. And well, in fact, in the end, after all this construction, we have managed to obtain a formulation which is completely free of any coordinate system. So everything is defined in terms of lengths. Angles can be calculated. There are no coordinates. So on the first glance, the question of whether we have holonomies or not in this kind of, when we define them or not, is not really a completely obvious question. Well, the consequence of discretization is that somehow a typical object from the point of view of geometry, which is curvature, is rather singular. It is localized in the hinges of this triangulation. And of course, well, I mean, here are examples of such a structure in 2, 3, and 4 dimensions. In fact, we do not see curvature directly. We can only observe it by trying to measure the angle which we obtain by going around a hinge and trying to figure out what is the deficit angle. And so, in fact, curvature sits in a very special points, not everywhere, but it's not a continuous variable. It's only located in the hinges. Well, after we perform this analytic continuation, we obtain a system which is Euclidean in some sense. Hilbert-Einstein action, when we calculate what it is, turns out to be to produce a real probability to every configuration. So the theory is somehow changed into a statistical theory of geometric manifolds, 4-dimensional manifolds, which are Euclidean. Well, we can measure a number of things. Well, it's very difficult. We still cannot solve it analytically, but we can very effectively study properties of such models using computer simulations. And we can measure a number of quantities. For a given set of Bohr parameters of a model, we can measure what are the numbers of particular types of simplices. Well, we can measure more interesting quantities, like what is the Hausdorff dimension of such an object. It's a statistical theory, so in fact, each amplitude is not really one particular manifold, but it's a sum, statistical sum over many manifolds, which are weighted with the probability defined by the Hilbert-Einstein action. We can, for such an average object, we can calculate what is the Hausdorff dimension, what is the spectral dimension of such object, and well, there are more localized observables since it evolves in time. We can also measure what is the profile of volume, how does it depend on this imaginary time. It's something which is very similar to the scale factor in quantum gravity. And in fact, well, what we would like somehow to do is it possible at all to relate the short range properties of such a model, which are very discrete, to a large scale properties which we hope will reproduce general relativity if we are looking at the semi-classical limit of a model. And in fact, it turned out to be quite successful. The model managed to predict that from the statistical point of view, depending on Bohr parameters of the model, there are many phases, surprisingly many phases, although the model is relatively simple. It has one phase which is particularly interesting, which reproduces a geometry of the de Sitter universe, Euclidean de Sitter universe. And in fact, we could analyze what is the behavior of the scale factor in such a theory. We could show that Hausdorff dimension in this particular phase is 4, and that the spectral dimension has a very special property that it shrinks to 2 for small distances, but gets 4 when we go to large distances. Well, these are global variables, so sort of all these results are based on measuring profiles of volume. We would like somehow to be more related to loop quantum gravity, maybe, and to say whether we can say anything about holonomies, about the distribution of curvature on such models. Can we, for instance, discuss some objects which would be more related not only to scalar curvature, but maybe to some elements of Riemann tensor? And in fact, we can try to come back to this discussion of holonomies in the context of manifolds which are constructed from these elementary building blocks, which are simplices. Well, I'll repeat here again that following Regge, these simplices are assumed to be internally flat. We have rotated our system to imaginary time. So in fact, they are Euclidean 4-dimensional simplices. If they are flat, properties of such system are completely defined by the edge lengths. And these edge lengths, as I have told you, they are in the model assumed to be rather universal. So that means the spatial and time links, they are the same everywhere. If we glue together such simplices along a face, which is a 3-dimensional face, all lengths in this 3-dimensional face must be the same in order to connect such two simplices, which is a rather obvious requirement. And, well, we do not need coordinate system from this point of view of our construction, but this doesn't mean that we cannot have it. In fact, we are completely free to use arbitrary coordinate system in each simplex. And since the structure is Euclidean, we can assume that we can choose a Cartesian system of coordinates independently in each simplex. So if we have two neighboring simplices and we want to connect, and we try to build a parallel transport from one simplex to another, first of all, what is the intersection of these two simplices? It's the face on which they are glued together. And in fact, since they are internally flat, a parallel transport in each of these simplices is completely trivial, because Levi-Civita connection vanishes there. So in fact, the only place where we can see that something happens non-trivial geometrically is exactly at the face, where we have to connect coordinate system in one of the simplices to the coordinate system in the other simplex. And in fact, if we look at it closer, you can realize that somehow the effect completely does not depend on how the path behaves in one simplex, how it behaves in the other simplex, and also it does not really matter at which point in particular the crossing takes place. So in fact, it only depends on the fact that there is a phase between two simplices, and we can imagine that in fact this connection is related to a connection between centers of these neighboring simplices, but this is in some sense irrelevant. It can be whatever we want it to be. And we know now how to connect two such simplices. We can connect many of them, defining coordinate systems in all of this in a sequence of simplices. And we can also define a closed loop, something like a Wilson loop, which will behave in a similar way as we discussed before. If we decide to change coordinate system in this initial point, we also have to rotate the effective matrix. These objects are rotation matrices. In fact, they may be not really rotation matrices, but they rather belong to a O4 group, maybe not necessarily to SO4, because we do not completely control the parity of coordinate systems in the neighboring simplices. However, for a closed loop, this should be SO4 transformation. If we have such a transformation, it belongs to some conjugacy class, and in fact, this conjugacy class is completely characterized for each particular loop is characterized by two angles. So we can always, if we have SO4 matrix, we can always block diagonalize it to this form, where in fact we have two orthogonal two-dimensional rotations parameterized by angles θ1 and θ2. By the change of variables, by rotating it, we still can change θ into 2 pi minus θ. We can exchange θ1 with θ2. But actually there are two obvious invariants. One of them is related to the trace of such a matrix, and the other to the trace of the square of such matrix. And from this we can determine at least cosines of θ1 and θ2 up to a interchange between the two. Well, in fact, just to see the problems which are related to this kind of structures, there is a special case where we have a rotation, very simple loop, which is a small Planck scale loop which goes around a hinge. And it can be also shown that each such a loop is always characterized by only one angle. The other angle is always 0. And in fact, this epsilon, which is here, depends on the rotations between which are typical structures of this around such a hinge. And in fact, it can only take one of the set of discrete values in this formulation which we have here. In fact, example which will be shown here is the simplest example, where we assume that spatial and time directions are the same. So in fact, we have regular simplices, and these regular simplices, they always have a dihedral angle, which is well defined by a product around such a face. Well, it is a solution of such a set of trigonometric equations. And so in fact, the angle which we will see here will be a multiple of this elementary angle. And we can see that in fact, the curvature, which we can define in the model locally, is discretized. So it's a little bit like discretization of momentum on a lattice. Here we have discretization of curvature. Well, so it shows that somehow on a short scale, we have a very quantum system, which is very far away from classical description. And we can ask the question, is it possible, is this discreteness important if we try to move away, if we try to consider objects which are larger on this scale? Well, and in fact, for this we can only rely on computer simulations. And what I will try to explain here is explicit measurement which we performed. And for this, well, first of all, we have to define somehow the coordinate systems in all simplices which are along the path which we will be considering. And, well, this means that we somehow define this set of coordinates in these simplices. Well, if we consider just two of them, two neighboring simplices, they will in general have a face which is common. Let it be 1, 2, 3, 4. These vertices are somehow labeled. And we need to find a transformation which leaves the lengths and angles on this face invariant. This is a very simple algebra well, I will not really bore you with the derivation, but actually on each face we can request that the lengths of the edges are the same. We can also define a vector which is perpendicular to such a face, and we have to find a transformation which maps one set of coordinates to another set of coordinates, and it's a solution of a simple set of linear equations which can be easily solved. And so in fact, this is just a technical problem which I will not really try to discuss here. What we would like to see, what we would like to test, is what happens with this kind of object if we follow a path which is long. And how to make this path long? We have a following construction that was in practical calculations which we are doing on a computer. We assume that system is periodic in this imaginary time with some number of steps t. And in fact, yeah, thank you. In fact, a particular example here is a system which has this t equal 80. And if you just look at what is the shortest path which one can obtain by connecting simplex with its copy after t steps, you can see that it has 320 steps. It can be, of course, longer if we allow for deviations. But it's a typically long loop. It's something which is maybe similar for the people who have experience with QCD. It was object which was called a Polyakov loop. So it's a loop which is closed by periodicity, by topological constraint. And what we can do is to try to measure on this kind of loops a set of, well, big sample, statistical sample of loops. And for each of them, we can try to determine the angles θ1 and θ2 and see what is the distribution of these two angles. And in fact, what we would like to obtain, well, since the loop is long, we would like to obtain a situation where, in fact, for such a long loop, this distribution should be statistical. So we should not really expect any specific signal. And in fact, this is the result of the measurement, of numerical measurement. Very nice plot of θ1 and θ2. And in fact, it is superimposed on an analytic function, which I have given here, which turns out to be nothing else but the Haar measure on the SO4 group. So, well, somehow maybe I would like to conclude here that, in fact, it seems to be possible that although we have such a discrete structure of angles at a short scale, we are able to obtain back a continuous, sensible continuous behavior. The only problem is that nobody really knows what information is contained in large Wilson loops, but this is a question to people from general relativity or maybe perturbative general quantum gravity. But in fact, we may define a set of completely new observables which we are working on, which are related to correlations between curvatures at various distances and rotations at various distances. And in fact, since we are dealing with holonomies, this also opens the possibility of introducing a new type of matter fields which we never considered before, which is a vector field, which is conformally with a conformal action, conformal derivatives. And then, in fact, if you, at least superficially, if you integrate out a vector field on such a system, you get effective action, which is a sum of all possible loops which can be constructed by all holonomy loops which can be defined on this kind of object. So this is a working project. And as you see, we have been thinking about Jurek's birthday for the past years, thinking of how we can present a connection between our results and loop quantum and gravity. And so let me finish here. Thank you very much, and happy birthday, Jurek.
Thank you very much. Some time for questions. Yes.
If we consider, can you calculate the elements of the Riemann tensor with this? For example, that one could check that Gauss-Bonnet combination integrated is really an integer that we should know what it is because it depends only on topology.
I think yes. Well, this is I mean this connection, as you have seen, is very singular. If you just consider it as a function.
That's why I'm asking. Yeah,
it's a delta function exactly on the face, and so. But anyway, if you define in this coordinate system which we have, it's a well-defined. Well, so you can define something like a Levi-Civita symbol on a connection. It's O4 transformation. So you have somehow to extract from this something which is exponent of some operator. But in principle, yes, I think you can do it. But we didn't do it. I think this is
because that would in a sense point to how well this approximates the.
Somehow the point of this exercise was rather to relate the short scale singular behavior with the long scale, and to see if indeed we can obtain back some information about continuum geometry from a short scale.
So I have a question, because you mentioned that when you have large 4 dimensions and then it turns out in the short scale to be 2 dimensions, and same thing happens in other approaches to quantum gravity. And do you think it's just coincidence or is it a providence?
Well, I don't know if it. Well, anyway, I think we were the first to discover this effect of the reduction of the spectral dimension, and very soon afterwards it was sort of found in a completely different approach, which was the renormalization group approach to quantum gravity. And well, let me say, I hope this is not a coincidence, but it seems to be a generic feature of all models which deal with general relativity. And so this may be is a hint that something really very important happens at short distances, that effectively quantum gravity becomes a renormalizable theory. Well, if it's really 2, then this would be a nice, although I'm not able to say anything more about this.
Could I ask a question about the analytic continuation that you mentioned early on? So as you mentioned in these causal dynamical triangulations, the relation between positive definite signature and Lorentz signature comes via an analytic continuation.
Yes. Well, so if you have Lorentzian signature, you can have this four-dimensional simplices have they have real time in the time direction, and there is some value of the action. You can calculate the angles which are given by cosines and hyperbolic cosines anyway. Then you can try to see what happens if you continue analytically this value of 80 to imaginary values. And it has to be done in a very precise way. And then hyperbolic cosines change into trigonometric functions, and the action becomes real. So in fact, there is a well-defined procedure which still preserves a notion of time. So in fact, although it's Euclidean, still we know what is the time ordering of the states for each configuration. So for each configuration, we can perform a rotation back in principle.
So I'd like to ask a two-part question about this, the general part and a specific part. The general part is that in many approaches to quantum gravity, we like to do calculations in positive definite signature and at the end come to Lorentz signature by analytic continuation. For example, in the scattering amplitude type calculations that were described earlier at this meeting. So the general question is, in causal dynamical triangulations, do you see this relation between Lorentz and positive definite as conceptually similar or conceptually different from how it might appear, for example, in scattering amplitude calculations? And the specific question is, in the calculations you showed today, does the continuation play a role?
Well, we never tried really to calculate similar quantities in the context in a formulation of in the Lorentzian, with a Lorentzian metric. And in fact, since our main instrument is a computer, we are sort of confined to a situation where we have probabilities, real things. And in fact, if we would like to formulate it, we can formulate it formally also in the Lorentzian signature, but then we have probabilities which are complex. And if we would like to measure anything on a computer, this becomes sort of hopeless. So in fact, the only way we can do it is to try to measure things in this Euclidean setup, and then try, eventually when we measure things, try to continue analytically the resulting structures and correlations back to Lorentzian. And in some sense, it's what we have seen, for instance, in one of these phases of the model is a profile which is very well defined by a cosine to the third function. So if you continue it analytically, you see this is just a de Sitter, a volume of the de Sitter space. So in fact, if you can continue it analytically, you get it to become a cosh to the third exponential growth of the in real time. So, but somehow this path between the original formulation and this semi-classical limit is quite distant. So in fact, it's definitely not the ultraviolet time, but it's some effective time which is produced by the model. And I must say, we are not really bold enough to really claim phenomenological consequences of this yet. But maybe it's coming.
Maybe one more question, if there is one. Yes, last question for the speaker.
So what do you hope to be able to measure concerning holonomies using this toroidal topology that you are recently exploring?
Well, we have this is a new set of observables which we never studied before. And in fact, well, we have only looked here. I discussed a situation where we looked at a holonomy along a time loop, which is something like a mass line. So in fact, but this is also a problem which was not completely studied because, well, I mean, currently we are discussing what are the structures like mass lines at all in the context of this kind of objects, but we can also define spatial closed loops. And if we have a toroidal topology, we can have spatial loops which are not on one period, but maybe you can go make several rotations, well, winding number loops with larger winding numbers. This is something which we are planning to do, but what will come out of it we still do not know, and we are waiting for results. So,
thank you very much again.